first define what a cyclic quad is. So a cyclic quad is any figure, and I'm going to just show you an example here. It's any figure that has a circle around it and four sides or four points touching the circumference. What closes this figure is the circle itself. So I don't need these sides to all be closed in order for that thing to be a cyclic quad. I just need to have a figure with a connected figure with four points on the circumference. Meaning that even this here can be a cyclic quad. Okay, because first of all, the interior figure is connected, and secondly, it has 4 points touching the circumference. So that is basically where we are going now. We are going into knowing theorems to do with cyclic quads. So we can have point from here to there, another from here to there, and then this and that. This one by definition is going to be a cyclic quadrilateral. I don't need any sides to be equal. L, M, N, O. Okay, so if this is a cyclic quad, in other words, if L, M, N, O is cyclic quad, then two things. First, O, okay, maybe I chose the wrong letter, but it's fine for now. Let's just leave it. O will be equal to M. Sorry, it's not equal to M. O plus M will be equal to 180. And L plus N is also equal to 180. Because what is this? It's the opposite angles of a cyclic quad are supplementary. So the sum of the opposite angles will be equal to 180. So if I'm using this, I would say opposite angles of cyclic quad. We can create the converse of this, right? So the converse of this would be, if I can prove that this plus that is 180 degrees, then this figure is a cyclic quad. And that is where most students struggle, is when they now have points that have no circle around them, and now they have to prove that those points will form a cyclic quad. So one way to prove that is by proving that a pair of opposite sides are supplementary. So you can say O plus M is equal to 180, prove that. Or you can say L plus N is equal to 180. If you've proven that, then you can now conclude that this is a cyclic quad. And if we are using the converse, we will just say converse opposite angles of a cyclic quad. That is, if we are starting with the 180 and proving that something is a cyclic quad. But if we already know that something is a cyclic quad, and we are trying to prove, and then we are making a conclusion that opposite angles are supplementary, then we use opposite angles of a cyclic quad. We are not using the converse. So we can call this theorem, I forgot, is it theorem 5? We can call this theorem 5. So this is not the only theorem that involves cyclic quads, right? There is another theorem that does involve a cyclic quad, and in this case we will refer to that one as theorem 6. It's also another way, if we are forced to prove a cyclic quad, that we can use. I'm going to use a similar diagram here, but now the difference is that I mean to extend this one. And then I will call this A, B, C, D, and then D is going to have a D1 and D2. Alright? And please don't expect this to be a D3. The only thing that divides an angle is a straight line, not a curve like this. So D2 is this whole thing. Okay? So what do we know? If A, B, C, D is a cyclic quad, then we know that, okay, we already know that D1 plus B is going to be 180 degrees, but better yet, D2 will be equal to B. So not only is D1 plus B equal to 180, but also D1 plus D2 is 180, meaning that B and D2 must be equal to each other, because D1 plus D2 is 180 because of angles in a straight line, and D1 plus B is equal to 180 because of opposite angles of a cyclic quad. Then it means B and D2 are also equal to one another. This, we said, is going to be theorem 6. And if this is theorem 6, the way in which it will be used, we will say exterior angle of cyclic quad. I do have another type of cyclic quad that I want us to pay a visit to, and then we will have, I don't know whether I should make it like a corollary. It should follow directly from something, but okay, maybe let's not use that for now. Let's just move on to tangent theorems for now. But then we are going to talk about that method of seeing a cyclic quad or proving a cyclic quad using angles in the same segment. We can use angles in the same segment to prove a cyclic quad, like this one here. We can be asked that A, B, C, D is a cyclic quad, and our job might be to prove D is equal to C. If I can prove that D is equal to C, then I've proven a cyclic quadrilateral. So yeah, let's do theorem 7. I'm going to call this one of the tangent theorems. So a tangent is any line that passes through, that touches a curve exactly once. We call that a tangent. So this here is an example of a tangent, and I'm going to call it tan, T-A-N. So I'm looking for my pen, T-A-N. And let's suppose I also have a center, which is going to be my O. I like my centers to be O. And then if I've got a line from center connected to the tangent, something interesting happens. So if TAN is a tangent, then OA is perpendicular to TN or TAN. So let's see. If TN, let me just call it TN because it's an extension, is a tangent, then, oh, different color, then TN is perpendicular to OA, the lines. So I can put a 90 degrees. You can even put it in the other side, it's fine, doesn't matter. So we say tan perpendicular to radius. Sometimes the radius might not be, this line might not just be a radius, it might be a diameter. So we can also say if there's an extension here, let me use a blue color. If there's an extension, then this is a diameter. I'm going to call this B. So it means BA is perpendicular to TN. So we say this is tan perpendicular to radius, if it's a radius, or tan perpendicular to diameter, if it's a diameter. So we can use either one depending on what we've just proven. Okay. The converse, we can use the converse. If I can first prove that there's a 90 degrees and I'm asked to prove that TAN is a tangent, then my job would be to prove a 90 degrees first. And if I can prove a 90 degrees first, I can make the conclusion that tan, or maybe I should prove that AB is perpendicular to TN. If I've proven that, then I can always now use the converse and say, therefore tan or TAN is a tangent. And if TAN is a tangent, then the reason would be converse tan perpendicular to radius, or converse tan perpendicular to diameter. We do have questions where we are asked to prove things like that. I want to do a Tanchord theorem as well. In fact, that is the one I would have thought of first. I don't know why I didn't, but I think Tanchord theorem must come out as a corollary. I'm afraid to do it now. Okay, it won't come out as a corollary. It's fine. It's a theorem on its own. But before we move on to Tanchord theorem, let's just continue talking about tangents with centers. So if I've got a center here, now I'm going to draw two tangents. I'm going to draw one that looks like this, place it there, and then I'm going to draw another one like connected to this one and make it touch at that point. Okay, let's say they touch at point A, or let's even use K. Okay. So let's say this is my point L and this is my point M. Then this can be our center, but it's, at this point the center is not very important. So what does theorem, I'm going to call this theorem 8. So theorem 8 tells us if KL and KM are tangents, then KL is equal to KM. Tangents at the same point are often equal to each other. They are always equal to each other. So we would say tangents, if we are to use this, tangents at a point. Okay, so that is what we could prove. So if in fact I extended, or I drew a radius here, and another radius there, then we know that this could have been a 90 degrees there, right? And somebody can even ask us to prove that OLKM is a cyclic quad. We've already proven that L is 90, M is 90. 90 plus 90 is 180. So since the opposite angles are supplementary, then it means OLKM is a cyclic quad. But that is not what we are doing here now. I was just showing you something, okay? I'm not saying we are proving anything yet. So that was our theorem 8. Let me move on to the next side. I intend to remove this, but maybe I shouldn't. Want to make sure that, okay, yeah, I knew it. Okay, all right. Okay, so I won't remove this, I'll just continue beneath it. So I think we were on theorem what? 8, so we are moving on to theorem 9, whatever we will call our theorem 9. In this case, I said I want our theorem 9 to be Tancourt theorem. So let's talk a little bit about Tancourt theorem. So if I've got a tangent, and then within the tangent I've got a chord that touches the tangent, that chord happens to produce an angle at the circumference. So I'm going to call this tan again. No, this is not what I meant to do. So tan, and then A, B, C. A can be divided into 1, 2, and 3, but I'm more interested in A1 and A3. So I want you to see that A1 is the angle between the tangent and the chord AC. But the chord AC happens to subtend the angle B. That is the first thing I want you to note. Another thing I want you to note is that A3 is between the tangent and AB. AB happens to subtend angle C. So if TAN is a tangent, then two things. Then A1, which is an angle between tangent and chord AC, will be equal to the angle subtended by AC, which is B. Right? Or we could say A3, which is between the tangent and AB, will be equal to the angle subtended by AB, which is C. Make sure you see how we make those follow-ups. We just use, when we are using this, we just say tan chord theorem. That is how we reference this theorem. And then we can move on maybe to a theorem 10. What is it? Can I think of anything? Okay, this is an ugly circle. What am I missing? I don't think I'm still missing anything. I've got theorems to do with tangents. I've got theorems to do with cyclic quads and the other theorems. But just note that this tan chord theorem, we can use the converse of it. We can prove that TAN is a tangent if we first prove that A3 is equal to C, or if we first prove that A1 is equal to B. And then we can now say, therefore, TAN is a tangent, and the reason for that is the converse of tan chord theorem, right? So just make sure you watch this as many times as it will help you, because the next thing we are doing is examples to do with this topic. This was only the cover of grade 11 theorems. We have not yet started with proportionality theorem, midpoint theorem, and similarity theorem. For now, we are only just covering the grade 11 theorems. Okay? Thank you very much. I hope this is useful to you.